So part 3 on the Theremin project, and you guys have been looking at this chassis a little bit. That's all this is a chassis. It doesn't look anything like a real Theremin yet, but we will get there. Also, I mentioned that we were using a circuit right out of an old hobby magazine, and that schematic is a good jumping off point for what we're going to be building. I like the use of the miniature tubes. Makes a lot of sense for a modest, middle-of-the-road type tube type project. Working with the miniature tubes, they're readily available, they're not super expensive. Again, this is a recycled chassis. It used to be a Harman Kardon school amplifier, so plenty of holes and sockets in it. And I said we were using 4 tubes, so why do we see 5 here? 1, 2, 3, 4, 5 tubes. Actually, this 5th tube here is the voltage regulator. I wanted the flexibility to try some 105 volt and some 150 volt voltage regulator tubes. So I actually have it wired up so it can take either the old style octal regulator tube or the newer miniature regulator tube. Another question people had is, what is this thing that's sticking up? Actually, this is just a handy thing that allows me to put the thing on its head and we can work on it. It's a leg just to even the thing out, and allows me to work on the bottom of the chassis and do soldering without having some issues. Okay, so let's talk about some of the stages that we're going to be developing. We know we need 3 oscillators. We need a fixed reference oscillator, we need a variable pitch oscillator, and we need a variable volume oscillator. In the magazine article, they were using Hartley oscillators for all 3, and they developed some tapped coils for the Hartley oscillators. The Hartley oscillator and the Armstrong oscillator both are very useful when you need to have a very active oscillator. By active I mean it's easy to establish the feedback and get the oscillator running. It's a very simple oscillator to get going, and also it's very reactive to the slight changes in capacitance that we're going to be introducing with our hand. We do not want a traditional high C, low L, super stable oscillator. We want an oscillator that has minimum C, maximum L, so that our hand capacitance influences the frequency as much as possible, at least on 2 of the oscillators. Now, one of the oscillators, the reference oscillator, he wants to be as stable as possible. So just to see if we can do it, I'm going to use a Colpitt's clap style oscillator for the reference oscillator. He's more stable because he uses capacitors for his feedback method, and very large capacitors actually at these low frequencies. We also need a mixer or a product detector, and I'm using the 6BE6 as they did in the article. The bottom of the 6BE6 is going to be the clap oscillator. The top is going to be the actual mixer in the heptode tube. The 2 variable oscillators are going to be Hartley's, as I said before, and they're going to be in the 12AU7 tube. So 1 devoted to pitch, 1 devoted to volume, both in this 12AU7 tube. Then we have the 6AU6 tube that's going to be doing both our audio preamplification as well as our gain control through the negative bias on its control grid. Finally, we have the 6AQ5, which is our speaker amplifier, which is going to put out a watt or 2 to drive a speaker so we can do practice with our Theremin. I want to touch on a couple of the practical aspects of the design, starting with the audio amplifier. I wanted to be able to have a line level output for the Theremin to drive various effects, such as echoes and loops. This is normal practice. But having a local speaker also makes sense. We'll call this a practice speaker. So I chose a very common audio tube lineup, a 6AU6 into a 6AQ5, both miniature tubes. To you audio guys, this should represent an extremely boring and non-controversial Class A amplifier chain. There's an additional requirement beyond a basic hi-fi amp. We need a preamp stage that can be gain controlled with negative bias voltage. That's because we have that volume control antenna, and that's how that works. RF amplifiers require a remote cutoff pentode like the 6SK7 or the 6BA6. These allow automatic gain control on their control grid. But for audio amplifiers in automatic gain control service, like the Theremin requires, sharp cutoff pentodes like the 6AU6 are generally preferred. A sharp cutoff tube will also vary its gain with negative DC grid bias, but over a narrower range. And the 6AU6 generally is more linear in audio operation than the remote cutoff pentodes found in many radio frequency circuits. Yes, the amplifier is very simple. Feel free to dress this amplifier out with 10 more parts and tone controls, but you're not going to gain much in terms of what the Theremin requires for linearity and response. Bias the tubes correctly, paying attention to the voltages on the screens and plates, and this amplifier will work fine. You might get 2 watts out of it. I've included basic feedback to smooth out the response and lower the distortion. I use quite a small audio output transformer, and the response dips below a couple hundred hertz. The addition of feedback flattened out the response and extended the 3 dB points both on the high and low ends. It also reduced distortion by a factor of almost 4. Overall, the amplifier mid-frequency gain was reduced accordingly in step with the feedback. How about the power supply? The power supply is entirely practical for any tube circuit requiring less than 15 watts of power. The transformer can be any modest center-tapped tube preamp type or broadcast band receiver type, capable of producing a couple hundred volts at least 40 milliamps and with a 6.3 volt filament winding capable of 2 amps. For instance, a 500 volt center-tapped 25 milliamp preamp transformer in a conventional dual diode center tap setup can produce 50 milliamps of current. That would be totally adequate. Hammond transformers like the 269AX or 269JX, they're a little bit bigger than a coffee cup, but you get the idea of the kind of transformer you need. Remember, the high voltage in these transformers can zap you. The high voltage DC can zap you. And don't forget the real danger, the AC line voltage itself. Always be careful with the high voltage in these tube circuits. The idea of our power supply is to produce 200 to 225 volts DC and 150 volts regulated for the oscillators. And of course we need the 6.3 volt filaments. By playing with the values of the power supply resistors shown, the series resistors in the power supply, and using either a conventional center tap setup or a single winding with a bridge rectifier, you can work with transformers from 200 volts single winding to 550 volts center tapped and come up with an output voltage that's usable. First of all, the power supply, fairly conventional. The only little bit exotic thing on the power supply is I'm using a separate filament transformer, because I wasn't sure that the small plate transformer had enough current to both provide the high voltage as well as the filament. Probably that was a worry that was unnecessary. That transformer probably is okay when we're only trying to develop a watt or two out of the 6AQ5 amplifier. So the first part of the Theremin is done, and that is the power supply and the basic 6AU6, 6AQ5 amplifier. Now we're going to be moving into the oscillator section of the Theremin. The next part of the development of the Theremin, and it's Theremin by the way, it's not Theremin, are the 3 oscillators that we need. One of the oscillators is the reference standard oscillator, or the master oscillator, and this guy stays fixed at 160 kilohertz. As we change this oscillator, we get the variable tone, and it's mixed in the 6BE6 tube. The other oscillator is over here. It's the volume control oscillator, and that's going to work through a filter and change the automatic gain control on a gain-controlled pentode. The clap oscillator is what I picked. The clap oscillator is a form of Colpitt's oscillator, and it really turned out to be a tougher nut to crack than I thought it would be. Doing it up at 7 megahertz or something isn't that hard, but down here at these very low frequencies, and this is 160 kilohertz was my target, it was a lot tougher to get a nice looking waveform out. You really have to pay attention to the impedances in the circuit, and it really caused me some pain to get the clap oscillator to run correctly. But in the end I was successful, and again we're using the 6BE6 pentagrid heptode tube. The bottom portion of the tube will be the oscillator, and the top portion is the mixer, the audio mixer. It's pretty stable. I've got a little bit of a random walk going with the oscillator, but it's very stable at 160 kilohertz. Here is the bottom side of the chassis with just about everything connected. So far I've tested the audio, the power supply, and all three oscillators are now running. I can tell you that the Hartley oscillators came right up, no fuss, no mess. The 12AU7, right out of the junk box, worked beautifully. The 6BE6 in the clap oscillator, however, was difficult to get running because getting the capacitors and the capacitor ratio right for the feedback was a little bit tough. So it was a great experiment, but I think I would stick with the Hartley for the reference oscillator after going through this exercise. So I'll let you look at the oscillators. I'll bring them up on the scope. We can look at all three of them. The volume oscillator is running around 450 kilohertz, and we've got the volume and the reference oscillator down around 165 kilohertz. I'm not going to fine-tune anything, but I have verified that I can move the slugs in all three coils and affect the frequency. You'll also see that I have the filter system here, which is a fixed filter around 450 to 460 kilohertz, and it's very sharp. I'm using a gimmick capacitor between the two tuned circuits. Anytime I get below about 5 picofarads, I think about using a gimmick because I can trim it back until I get the coupling I need to get the shape I need on the filter. And it's a lot better than substituting 10 different capacitors till you get what you want. The filter is undercoupled. We do not want a double hump. We don't want a flat filter. We want a very sharp filter because we're going to be running up and down one side of that filter, and that gives us the detected RF. That gives us the RF we're going to detect to affect the volume control on the control tube, the 6AU6. First we'll take a look at the clap oscillator. Nice sine wave coming out of the clap oscillator. Hope you can see that. Let me kill the lights. Okay. On the front of the scope probe I have a 0.01 1 kilovolt disc capacitor just for safety. Let's go over here to the pitch oscillator. Looks pretty good. And a similar frequency. Let's take a peek. Very nice. And let's run over to the volume oscillator. See if we can get on the volume oscillator here. Right over here. And the volume oscillator is running a little higher, but it's also a nice sine wave. So, all three oscillators running. Let's talk about coils. This is one of the touchier subjects when it comes to RF projects, and the Theremin is certainly RF based. There's a lot of fear when it comes to winding your own coils for specific purposes, especially where you're trying to hit frequencies on the nose for a project like this. The kind of coils you need to operate at lower frequencies, and by lower frequencies I mean between 100 kilohertz and say 3 megahertz. You need to have a coil that's compact enough to fit into your chassis. We could be making these coils out of pieces of PVC, air-wound, solenoid style, but the whole thing would become so large it's not really practical anymore. So we do like to use ferrite slug-tuned coils, and typically I like to get my hands on surplus slug-tuned coils. They're out there, and lately I've been attracted to the old TV coils, the ones that come out of the old TV sets from the 40s, 50s, and 60s, and especially the horizontal oscillator coils, the ones that have the big winding on the back of a few millihenries. Those are useful for a lot of things, but they have a nice big slug inside, and those make excellent foundation for winding these low frequency coils. So starting with those TV coils is not a bad thing. Usually what I do is I strip off all the windings, and if I want to hit the broadcast band, I just usually throw on about 100 scramble wound turns of something like, number 26 or number 28, and 9 times out of 10 I can hit the broadcast band with that. If I want to operate a little lower in frequency, let's say I need about 500 microhenries or so, then I'll put a couple hundred turns on the same form, and 9 times out of 10 I'll, with a fixed capacitor, be able to hit the frequencies quite nicely. And that's just what I did with these coils. I have the final inductance values recorded on the schematic, but as you can see, they're very simple scramble wound coils with some pretty heavy wire on them, and I just take turns off until I hit the right LC combination to hit the frequency. Now with the Hartleys, however many turns that you have on there, if it's 100 turns for instance, I usually have the tap up 25 turns. If it's 200 turns, I put the tap up 50 turns. So it's kind of like a 25% rule with the Hartley. It's usually more forgiving than that, though. You can probably get away with 15%, and the Hartley would still have enough feedback to work. It's a pretty flexible oscillator. But I'd like to tell you exactly how many turns to put on, but I don't know the answer to that because every form that I use is a little bit different than every other form. So I know to some of you making inductors for these circuits is probably the hardest part. The fastest way to approach the inductors is to select the frequencies you want to use. That's the first thing. We want to pick 2 unrelated frequencies, like 455 kilohertz for the volume oscillator and 585 kilohertz range for the pitch oscillators. These frequencies are not harmonically related, and they're far enough apart not to react with each other, as long as we get some decent spacing between the coils, a few inches. I originally selected 160 kilohertz for my pitch oscillator. Later on, I raised this into the broadcast band to get more hand sensitivity. Then, after you have your frequency selected, you need to select the capacitance values that you think you need. We want small c at these frequencies for the pitch oscillator. And we want a small c type situation for the volume oscillator. So I would say 100 to 220 picofarads would be a good place to start for those caps. Plug the caps and the frequency into the resonance formula, and you're going to get something in the hundreds of microhenries as an answer on the inductance. There's many ways to trim in the coils and to get the prescribed number of microhenries, be it 200 microhenries or 500 microhenries. I like to use the scope method, where you resonate the coil with your capacitor of choice, and you usually feed it with a 10K resistor off the generator, and then you just look on your scope for the peak. Other people have good inductance meters, and there's even bridges out there, and probably the hardest one is the one I like to end with, which is running the oscillator itself and measuring the frequency with a scope or counter. If you're doing cut and try with that method, it can take a while. But once you get in the ballpark, that's the way you actually check your circuit. With the clap oscillator, you want a high C, low L. So actually I used a smaller inductor in that case, and it turned out to be around a 470 picofarad cap to resonate the clap oscillator. This also lent itself towards using a trimmer on the clap reference oscillator as my fine pitch control. So you may be wondering how the volume oscillator causes the audio gain to be reduced. There are several circuits that could be employed, but cutting off the gain in the control grid of a pentode with some negative bias is a pretty effective method. If you consider that we are changing the frequency of the oscillator by several kilohertz, all we need is a circuit to detect it. A simple bandpass filter with a couple of lightly coupled sections can give quite a sharp response. What if we ran the signal against the edge of this response curve, which we've carefully positioned a few kilohertz lower in frequency? Then that resting frequency when we had our hand far away, then we could see the output amplitude rises as you bring your hand closer, forcing that frequency lower. A simple negative voltage doubling detector turns the rising amplitude into bias, and bingo, we have gain control. Again, you could just as easily do this with all kinds of solid-state devices or even other tube circuits such as differential amplifiers. So let's look at the volume control circuit itself. The oscillator's output is taken off the cathode, which is a fairly stable point on the oscillator. Very light coupling is used to the bandpass filter, just a few picofarads. You really need to tune the filter to get it lined up properly, so I've included some cheap $1 plastic trimmers across the resonating caps. So these are about 50 picofarad trimmers across some 100 picofarad resonating caps. The particular resonators that I found were 1 millihenry chokes. The very small capacitors in the filter can be store-bought, or you can make them out of gimmicks, which are twisted wires that give you a few picofarads of capacitance. The diode detector was loading the output too much, and I had to relent to a cathode follower. Really, I needed a buffer between the high impedance of the filter and the low impedance of the diode detector. So this circuit happens to be a modified cathode follower. It's self-biasing, and it gives you a little bit better performance than just hanging a resistor off the cathode. You get a lot more swing. Yeah, one more tube. I know some of you are complaining. We already had too many tubes, and here I am adding another one. This could be half of another 12AU7, or we could start combining stages in 6U8s or other double tubes. I didn't go that far. I had the space. I simply added another triode. I have the Theremin just warming up now. Basically, I want to control the volume using the 6AU6 tube, and by putting a negative 8 or 10 volts on it, because there is a 2 volt fixed bias on the cathode, I can cut the tube off and I can control the volume with the feedback detector. So now I'm just putting a negative voltage on it manually, but it's taking a while. Why is it taking so long for that to mute? And I think I just got an idea that's pretty simple. I think it's the coupling capacitor against the resistor that's going to the bias circuit. I think there's a time constant there. So the next thing I'm going to try is to reduce the value of the resistor and to reduce the value of the capacitor and see if we can't speed this up a little bit. Okay, I've reduced the coupling cap. It was gross. It was a 1 microfarad connected off the 500K volume pot. And what I think was happening is the 560K resistor that's on the grid of the tube was trying to discharge that capacitor through the 500K volume pot. So you effectively had like 1 meg against a 1 microfarad capacitor, and there's a time constant there. So the tube was not changing its bias instantaneously. So now I've reduced that down to a 0.02 coupling cap. I haven't touched anything else. Now when we put the -10 on there, it's pretty much instantaneous. So mystery solved on the gain control for the sharp cutoff pentode, the 6AU6. When I start one of these videos, and I'm in 2 videos, and still I'm not sure if the system is going to work or the circuit is going to function, I'm kind of putting it out there. There's no guarantee of success, and all I'm going on is old schematics and good faith that we'll be able to solve the problems one at a time. That's the way it is with this Theremin project. I've already had to make some adjustments that I wasn't counting on, and that's how you learn. First of all, the oscillators, which I originally had set for, you know, the 160 to 170 kilohertz for the pitch antenna, pitch oscillator, and 455 kilohertz for the volume oscillator. I found that the pitch oscillator was not giving me very good sensitivity. And by sensitivity, I mean distance to the antenna. So this is a child's cross-country ski pole, which I'm going to use as an antenna for this demonstration. By sensitivity, I mean how many hertz do you get per centimeter of closing the antenna with your hand. As I close the antenna, the frequency is going to go up. I would like to have control at least out a meter all the way in to where I just about touch the antenna. So what I found was that 170 kilohertz, I was getting control right in this range here. Didn't have much sensitivity. So I increased the frequency, broke the rule that I said in video 2 where we should stay out of the broadcast band, and I brought the pitch oscillator up to around 580 kilohertz. And I found that, yes, indeed, the sensitivity of the system has gone up. That's just an example of some of the things that have had to change to make the Theremin actually usable. I have this nice surplus Radio Shack 6x9 car speaker, which I'm using to test the system. Okay, so we have the Theremin. This is not bad sensitivity. Yes, this is a child's ski pole. A child's ski pole makes a good test antenna. I have not put any loading coil in here, and of course we're surrounded by metal. This is not the way you're supposed to test a Theremin, but it does tell me I do have some sensitivity, and I can lower the volume. So we are making progress on the project. Okay, a little bit of detail on the inductors and winding those coils. Remember that your particular coil form and slug may be a little different than the ones that I was able to salvage, and you'll have to increase or decrease the number of turns, maybe as much as 50 turns plus or minus. So for the Hartley tap, remember, between 15 and 25% of the coil for the tap up from the ground side. For the volume oscillator, I was targeting 426 kilohertz. Ended up with a resting frequency of 430, and just touching the antenna, I got it all the way down to 415, so I got some really good response on the volume. For the pitch oscillator, I picked 575 kilohertz as my resting frequency, with the frequency going down to almost 5 kilohertz down from that, so down to 570, and that one was 150 turns tapped at 25 turns, and I used a 200 picofarad cap. If I had maybe gone up to 175 turns, maybe 200 turns even, I could have brought that down to a 100 puff cap, and I might have gotten even more response than 5 kilohertz. For the reference oscillator, for the clap oscillator, I didn't really need a tap at all, so I simply wound a little more than 100 turns on the form, and that seemed to resonate just fine with a 470 puff cap, and there was a 10 puff trimmer tacked on there as well. The Theremin is getting very close to the point where I want to start to package it. The last thing left to do is to build the loading coils. Basically, these coils tune the antenna to resonance and effectively increases the amount of voltage on the antenna, which makes the sensitivity increase, and if this resonance point is put just below the parallel resonance of the oscillator's tank, you can get some linearization. That's what I'm going for. So the next step is to build the loading coils. There will be one loading coil for the pitch antenna and one loading coil that's going to go over to the volume antenna. The other thing that's happened with this since the last video is instead of 170 kilohertz for the pitch frequency, I've increased it to about 580 kilohertz up in the broadcast band because I wanted to get more sensitivity with the unit. So I have succumbed to the raising frequency solution to try to improve the performance before we build a cabinet and try to do the final packaging, which is very important, by the way, because until you have it in the package, you don't exactly know what stability is, and there will have to be some tuning involved once we get it into the package. But I'm very happy with the unit as far as stability goes. It's very stable. It, once warmed up after about 10 minutes, it's totally solid. And I'm pretty satisfied with the volume. That will improve, of course, once we get it properly built out with the loading coil. Not too bad. Pretty stable. Okay, that's it for this video. The next time you see this thing, it's going to be in a case. And hopefully we'll have the proper antennas on it, and the finished product will actually be something that is playable, meaning someone could actually play the theremin as a musical instrument.